Hello everyone, my name is Colin Coates. I'm the product manager for Andor for the imaging cameras. So I want to welcome you to today's webinar on our new iKon XL very large area CCD platform. And thank you for your attendance. Okay, the agenda is going to be quite simple. Before I get into the bulk of the presentation, which is on the new iKon XL, I'm going to preface that with just a little bit of a recap on some of our other solutions that can be used for astronomy. So I'm going to talk a little bit about solutions that we have for fast time resolution astronomy. Now, we actually had a dedicated webinar on fast time resolution astronomy about 3 or 4 weeks ago, which can still be accessed online, so I would encourage you to do so if you haven't viewed it. Then I'm going to talk about generally what our slow scan detector solutions are, which will lead me nicely into the very large area CCD platform, which is the topic of the webinar. So, but just very briefly, for those who aren't familiar with who Andor is, we're actually now part of the Oxford Instruments Company. Um, Generally, we're considered as the pioneering and leading high-performance light measurement company. Um, we're actually a spin-out company from Queen's University of Belfast from the physics department back in 1989, so we're over 25 years old now. Right now, within Andor, we have 357 direct staff, and of course, we're selling largely through a lot of distributors right around the globe as well. Um, if you take our product portfolio as a whole, it can be split into the areas shown here. So there's low light imaging, so the low light imaging cameras. We also offer a lot of modular spectroscopy solutions as well um, for many different types of research. We actually have a software division within the company also, primarily focusing on software, very high-end visualization software and rendering software for microscopy. And then finally, we have an actual microscopy systems division, providing very complex high-end modular microscope solutions. But today, we're going to focus on the low-light imaging cameras for astronomy. So as I said, I'm going to first of all dip a little bit into some of our fast time resolution solutions because they are relevant for some niche areas of astronomy for sure. And the first technology I'll cover is electron multiplying CCDs, EM CCDs. So they were introduced actually more than 14 years ago now as a high performance alternative to CCDs at faster frame rates. So the problem with taking a slow scan CCD effectively and trying to push it to a faster readout speed is that the read noise increases, which very much is to the detriment of the overall sensitivity of the detector. So EMCCDs address this by inserting an amplification technology, and I've got that animated effectively. At the bottom, there's a little structure in the readout chain called the gain register. It applies a high voltage across one of the phases of transfer, which creates in turn a high electric field, and with that comes the probability of creating an extra electron through a process called impact ionization. So when you do this in serial over more than 500 pixels in the gain register, 500 transfers, then you do get quite a sizable potential for amplification of the signal. So even a single electron generated from a photon can be amplified to say about 1,000 electrons, which more than overcomes the read noise floor of the CCD even at fast speeds. So that's what renders the EMCCD single photon sensitive, and that then can be combined with back illumination. So basically you have the potential for more than 90% QE combined with single photon sensitivity, even at fast frame rates, which is what makes them quite an exciting technology for more rapid, but still very low light applications. And I've listed there on the right hand side some of the applications which actually have been benefiting throughout the years within astronomy from EMCCD detectors, from lucky imaging, adaptive optics wavefront sensors, high time resolution astrophysics, for example, in pulsar studies. They've been detectors in solar astronomy, and solar cameras tend to need to go fast as well. And they've even been used as customized high-end guide cameras, and I've got a good example of that to be shown. And this is the very example actually. This is the NASA SOFIA project, which many of you will be familiar with. It's the customized jet aircraft, which is then can be deployed to very high altitudes, obviously, and is obviously also very, very mobile as an observatory goes. But with in turning a plane into an observatory, that carries a huge amount of stability problems, as you might imagine. So you need to have some very exceptionally robust work done on the stabilization mechanisms and in the guide cameras in particular. So the iKon 888, which is a 1 megapixel EMCCD, was customized to be used then as the guide camera on the Sophia Observatory, and actually it is then used as the science camera also, where visible detection is required. So there's a couple of quotes actually from the Sophia website regarding this camera. The camera works as expected, and compared to the previous camera which is in place as a guide camera, we've improved the signal to noise by a factor of 100, and this has enabled them to successfully guide in more than 95% of the fields now. So that's been a very, very successful project for Andor. Raven is another good example. It's based at the Subaru telescope, and actually it was featured in the webinar of a few weeks ago that I referred to, so it's worth going back to listen to more detail on that. It's a very exciting project where they've used multiple cameras to extend the applicable field of view available from an adaptive optics setup. So you get really amazing resolving power over an extended field of view using this unique setup. So before I move away from fast time resolution, I'm going to briefly touch on scientific CMOS. So it's a more recent technology than EMCCDs, and the technology is about 5 or 6 years old now. And it's relatively unique as a fast time resolution technique, in that you're really able to achieve a lot of high performance specifications without necessarily trading off one against the other. So I'm exemplifying what I mean there in terms of the currently available sensors that are in our cameras, and our cameras are called both the NEO or the Xyla SCMOS. So you can get down to even less than 1 electron now with these devices, and you can do so while maintaining a very, very fast frame rate. So I've actually got their frame rates up to 100 frames per second full frame. And bearing in mind, these can be from 4.2 or 5.5 megapixel arrays. So typically the pixel formats are larger than what you would find for commercial EMCCD. So it does have that resolving power and field of view advantage as well. Couple that with low noise, fast speeds, and actually there's a on-chip mechanism to give you extended dynamic range, especially for the relatively small pixel sizes that we're talking about, which is 6.5 microns currently. The mechanism itself enables you to achieve low noise and the full well depth within one scan, which typically can't be done with CCDs. And I say typically there because there is one exception, which I'll talk about later. A recent improvement to the SCMOS technology has seen us boost the quantum efficiency even further. So even though these are not back illuminated devices as yet, we're achieving now up to 82% quantum efficiency from a front illuminated micro lens device, which is quite unprecedented. It's a quantum efficiency level which has never been achieved before from a front illuminated CCD. And finally, because I know this will be important for some applications, that they're available with both rolling and global shutter options. This slide just gives you an indication of the level of read noise improvement you can expect from an SCMOS relative to here I've got a 5 electron noise CCD. So this is a light tight imaging rig. The background photons are very, very low, so it puts the emphasis on the read noise of the detector as being the real detection limit. And you can see here, obviously, when you go to a much lower noise SCMOS, it cuts that read noise graphs well down, and you get much better contrast under these identical illumination conditions. And this is quite low light. This is about I estimated 32 photons per pixel. I mentioned the frame rates already, but this is simply showing that yes, you can get up to 100 frames per second at full frame and rolling shutter. It's actually half of that in global shutter because there are 2 readouts required to operate in global shutter mode. But it shows you also that you can really push the frame rates very fast when you go to smaller and smaller sub-regions, and that's entirely possible as well. Now, the question does come up when you have fast time resolution applications, should you use SCMOS or EMCCDs? And generally, that is a matter that if, it's a really matter of photon flux. You would typically use an SCMOS if you weren't challenged at by very weak signals is the shorthand answer, because SCMOS can, because it's a multiplex readout, many pixels are read out in parallel, and you can get higher resolution and larger field of view. SCMOS holds an overall flexibility advantage, but it can't be ignored that many applications do require very low light um, uh, detection capability, and you will find a crossover point in the signal to noise plots versus photon flux, at which EMCCD takes over as you go to lower and lower light. So I mean, as it turns out, many of the applications really that EMCCDs were originally purchased for still tend to operate better with an EMCCD than with an SCMOS. So there's been an extent of cannibalization of the EMCCD market by this new technology, but still there's a very robust expectation that EMCCDs will still perform for a good chunk of the low light market. So moving on, I want to now move towards the slow scan CCDs, which is more aligned with the primary topic of today. So when you can take your time to read out, basically, there's very little substitute for a really deep cooled, low noise, back illuminated CCD. As long as you're not trying to go with faster frame rates, it's hard to replace the quality and detection sensitivity of a good high QE low noise CCD. And this is very typical of that type of camera. This is our traditional iKon range cameras. This is the iKon L we're showing here, not the XL, the L, which houses up to a 4 megapixel sensor, and that specifically because many of you will know the sensor codes. That's the E2V 4240. So 4K by 4K with 13.5 micron pixel size. What Andor have always been very good at in achieving low noise floors, especially on slow scan long exposure applications, is cooling. We can cool this sensor down to -100 degrees using thermoelectric cooling, so no liquid nitrogen, no compressed gas, cryo Tiger type cooling required. So that of course opens the possibility to maintain very long exposures for very weak signal. And then also we make a good job of minimizing the read noise and extending dynamic range that way as well. Here's a good example. Sorry, before I go there, a recent innovation that we launched with the iKon L 4 megapixel camera is shown here, and it's utilizing a new QE profile. Basically, we call it the BEX2DD, and it offers the highest and broadest quantum efficiency curve that you can get for this type of sensor. You can see it in the solid red line there. So this green line, the solid green line, the BV, is what people would typically deal with from a standard mid-band AR coated back-illuminated CCD. But here we have this solid red line, the new sensor, and there's 3 different technologies actually contributing to the broadness of that QE curve. For one, it's deep depletion, so that effectively creates a longer path length for the near-infrared photons to travel through, and increases their chance of absorption by the silicon, and that increases then the QE in the near-infrared. It's based on what is called enhanced silicon as well, which actually lifts up the QE in the blue. And on top of that, there's a dual layer AR coating on it, which generally broadens the QE. So there's 3 different technologies working together to give this really broad QE curve, and this already is proving very popular for slow scan astronomy applications. A good example, it goes back a bit, but it's still very relevant, is the Super WASP. The Super WASP was built on the iKon L cameras. And Super Wasp, I'm sure many of you have heard of it, is a transit approach to detecting extrasolar planets. It's been very, very successful. Um, it's built on using wide-angle lenses, and arrays of cameras in both the northern and southern hemisphere are used to basically image the entire night sky continuously. So it's looking for slight dips in the photometric profile as an extrasolar planet transits in front of a distant star. And then, of course, that will give you a candidate for an extrasolar planet, and then the big telescopes, of course, can be trained on that for more detailed spectral analysis, etc. But Super WASP has been very, very successful in facilitating the identification of many, many new extrasolar planets. Um, some of you might know that Andor actually acquired the company Apogee about almost 2 years ago. So this is just to remind people of that, more or less, that the Apogee cameras that people have been used to are now still available but through the Andor website you will find them. The Apogee website, as it was, ccd.com, is more of a landing page currently, and all the details are now housed within the Andor website. So Apogee is really an extension of the Andor product portfolio for astronomy. It's a very wide range of sensors, up to 16.8 megapixels, so some very high resolution options in there. And within this range, we offer USB 2 and Ethernet. And all the cameras are now manufactured in Andor's Belfast factory, alongside all of our more traditional Andor cameras. The portfolio I'd like to present here, or highlight at least, on Apogee is the Alta and the Aspen. So the Alta is the more long-standing camera range from Apogee. It's been in the market for quite some years through a number of different revisions, and it cools to typically minus 35 degrees or delta 60 if you want to look at it that way. It's a range of both full frame and interline sensors, and there's 16 sensor options in total. As I said, up to 16.8 megapixel, and it's USB 2. The more recent camera line from the Apogee range is the Aspen. It's similar to the Alta, really, except it cools that bit deeper. You'll see minus 45 degrees there. And it adds also an Ethernet interface, which can be very relevant for some astronomy applications. Just to pull out one specific example, because I feel it's relevant for the topic that we're talking about today. This is a 16 megapixel, so a 4K version of the Aspen called the CG16M. And actually, this is the most popular seller for astronomy within the Apogee range of cameras. It's 9 micron pixels, so not as large as the E2V sensors we'll talk about today and the iKon XL, but still, it is nevertheless a 16.8 megapixel device at a more favorable budget, let's say, than the iKon XL cameras, which we will talk about. It's not as high end. It's not as nearly as deeply cooled as the iKon XL. Doesn't have the quantum efficiency, but nevertheless, it is still a very viable 16 megapixel solution that we can offer. So on to the primary topic now, the iKon XL. So this is based initially on a couple of popular 4K sensors from E2V. So these are large area 15 micron pixel size sensors. So the sensors themselves are more than 60 millimeters by 60 millimeters in dimension. So we're talking very large area devices. And we're very excited about what we've done with this product. There's a number of very innovative things that we've launched as part of this camera platform. The one we're probably most proud of is the first one I'm going to highlight here, and we've called it cold space technology. There's actually an underlying patent pending technology behind our capability here, and the capability really is to take such a large area detector and be able to thermoelectrically cool it down to minus 100 degrees. So we can offer really unprecedented deep cooling without the need for liquid nitrogen, without the need for compressed gas cryo tiger, because as we all know, there can be some reliability issues in these types of technologies in the past, and without the need for repumping. It uses Andor's tried and tested and well proven ultravac vacuum technology as well, so there will be no repumping requirement. So it's a good maintenance-free detector is a good way of describing it, but still without compromising on the performance aspect. Another leading innovation we've brought into this as well is what we've called extended dynamic range technology. So I mentioned earlier how the SCMOS actually had on-chip technology to enable you to achieve the lowest read noise and the maximum well depth in one scan. But so far, CCDs have not been capable of doing that. Normally with a CCD, you have to make a choice. You have to either optimize a CCD for low noise, the low read noise, or you have to optimize it for the max well depth. But in optimizing for the max well depth, you would typically compromise quite considerably the read noise. So that either way limits your dynamic range, either at the bottom end or the top end. Now, so this is what we've done differently. With the iKon XL, we actually have put in some know-how into our camera, which we feel is quite unique, which lets you access the lowest read noise and the maximum well depth in one image. Now, that's quite interesting because it carries a very unique implication when it comes to how to digitize the extent of dynamic range we're now talking about. So I'm going to use the example here of one of the sensors that we're using, which is the CCD231-84. It's the one E2V would call the Astro version of the sensor, which is their terminology. But basically, it offers a hugely impressive pixel well depth of 350,000 electrons, and it combines that with a very low noise of 2.1 electrons. So these are specs taken from the E2V datasheet. So when you do the simple mathematics of dividing the well depth by the detection limit, which in this case is the read noise, you get 166,000 to 1 true dynamic range. Now, when you digitize this, you don't want to undersample the dynamic range, you want to oversample it. But if you applied 16 bits of digitization to it, which is just over 65,000 gray levels, that's not nearly sufficient, nor even a 17-bit, because that's about 130 something thousand. 130 something thousand gray levels. We actually have to go to 18 bits digitization to oversample that dynamic range. So we feel that's quite a unique aspect that this technology brings. So we're offering that basically as a choice. Then within the camera, you can choose 16-bit or 18-bit depending on the circumstances of your readout. So a few further details about the platform itself. So there are actually, as well as 2 different sensor variants initially, there are 2 different build variants of the camera. One we've called the deep cool version, which is the version that liquid cools down to -100. So that's the version you would look towards if the cooling was extremely important. Then all you have to bear in mind is you have to provide a liquid flow to it, and Andor can actually help down the line advise on what you need to do there. The Flexi version, as we're calling it, offers both liquid cooling and air cooling. So the liquid cools to -75 and air cools to -55. These sensors have 4 parallel readout ports, so we're very much making use of those as well and balancing them very well. We have introduced connection flexibility, so there's both USB 3 output and a direct fiber optic connection as well, long distance fiber optic connection, which I know can be very relevant at some observatories. I mentioned there we're balancing the amplifiers very well. I'll come to a later slide specifically on that to describe it in a bit more detail what we're doing. Another thing we've been asked for by astronomers down the years actually is iRig-B GPS timestamp. So we felt we would introduce it in this camera. So it gives time and positional accuracy and actually can be quite useful for networking multiple sites of observation. I've mentioned already a low maintenance advantage. So generally, yes, I've talked about the lack of need for liquid nitrogen or cryocoolers and no repumping. We've actually even extended this to make sure that we have built a very, very easily replaceable shutter into the cameras, because let's face it, no shutter is spec'd for infinite usage. Sooner or later, the cycle spec of that shutter will be knocking on its own lifetime specification, and it's going to have to be replaced at some point. But we've preempted that. We don't want to have our users, take their cameras off the top of a high mountain in Chile and have to send it back to one of our Andor's hubs around the world for replacement of the shutter. We'd rather give you the capability to easily replace that shutter on site. So that's what we've done, but we've specifically engineered a field replaceable shutter into this camera with that in mind. Okay, I'll talk about the two sensor options now that are in the iKon XL. So basically we have two models accordingly. The iKon XL 230 is the first one. It uses the CCD 230-84. Again, cools to -100 as far as the camera is concerned. And the distinction will be its read noise is 4.5 electrons and its well depth is 150,000 electrons. And if I look towards the QE curves that are offered in this sensor, we have the standard blue one here, the mid-band coated, what we call the BV sensor. But actually for some niche applications, you may also be interested in the BB sensor. In fact, we recently took an order for one of these cameras within the past 2 weeks, which specifically ordered this more blue optimized BB option. Then we have the iKon XL 231. So I've already mentioned it's based on the CCD 231-84. Its main distinction then becomes the read noise and well depth, and this is what then puts the emphasis on this unique extended dynamic range capability to achieve your read noise and high well depth in one scan. Interestingly, you can get this sensor in both standard silicon and deep depletion. So I'll show you the curves now. If the top left-hand curve here is the standard silicon, and you can see the QE options are a little bit more extensive. We actually have one called the BEX2, which is based on enhanced silicon to enhance the blue and has the dual AR coating. Then if we take that to the extremes down here, I mentioned the BEX2DD in the context of the iKon L. We offer it on the iKon XL as well now. So it's got enhanced silicon, it's deep depletion to enhance the near infrared, and it offers the dual AR coating. And we offer also a more traditional deep depletion sensor, this BRDD, without the dual AR coating, without enhanced silicon. So quite a bit of choice in there, really. Just to show you the dimensions and weights of the deep cooled. So the deep cooled, as a reminder, is the -100 liquid cooled version versus the flexi version, which does the liquid and air cooling. So the deep cooled is by far the heavier of the two at 12 kilograms and a 200mm body diameter. The flexi version is lighter at 8.25 kilograms with a shorter body diameter as well. Now, I'm saying body diameter, but the front face where the shutter is will still be of the same diameter, which is 200. Okay, just a note on what we're doing when we're trying to balance the 4 different quadrants of this sensor. We've really gone to a lot of effort here to try, and even before you have to apply any real-time correction to do balancing, we're really trying to make sure at the raw data level we're doing as much as we can to ensure that the quadrants are as balanced as possible. So basically we have 4 physically separated ADCs and preamps with separate power supplies for each quadrant. And with that, we actually have tracking stability. There are 4 circuits maintained at the same operating temperature and experience the same operating conditions. So we try to really balance the operational conditions of these quadrants as thoroughly as possible. And then we will have ADC correction. So we'll use offset and gain correction algorithms to compensate in real time within the camera FPGA the signal between the quadrants. And if you don't want us doing that, we can turn it off. I know many users prefer to do their own balancing, so we'll easily offer the capability just to take the raw data as is and let you do your own balancing real time. Just a bit of a discussion point around how much cooling is enough. So yes, we're cooling to -100, and you could argue that in extreme cases you may want to use liquid nitrogen to push it, down below 120 or whatever. But there's a few things to bear in mind which are as relevant to astronomy as to any other application. Well, one is some typical dark current profiles of AMO type sensors. You can see here as you cool down, it's not really a linear relationship beyond a certain point. Once you get to minus 80 degrees, the dark current actually starts to level out more so. Not quite level out, but it's a case of diminishing returns as you continue to cool. So it tends to flatten off that bit more and more. So it really says that if you cool to minus 80, minus 90, minus 100, that tends to be enough to stretch the minimum dark current out of the sensor anyhow. Uh, putting more elaborate technologies in place to cool beyond minus 100 will be a case of diminishing returns. And then we often have to bear in mind what is the level of the sky background. The universe itself has a level of background. There's a diagonal background, and you have to consider, is that background going to be larger than your dark current anyhow uh, within an observation condition. So that's always worth bearing in mind, and always worth doing an analysis as to what level of background we're really talking about and how really important is it to squeeze every last sub electron of dark current out of the dark current spec. In terms of the sensor choices, so we have formally launched the camera on the CCD230-84 and the CCD231-84. However, I should point out we actually have shipped a camera so far using the CCD203-82 from E2V. Again, it's 4K by 4K, but its primary difference is it's got a smaller pixel size. It's actually a 12 micron pixel size and a slightly smaller well depth accordingly, 100K electrons well depth. And it was used. It can be popular within astronomy actually for a shell spectroscopy. The smaller pixel size tends to suit the resolution requirements of a shell spectrograph a bit more. The reason it's not a standard product right now is that the sensor actually isn't always available from E2V. The availability of this sensor can be a bit sporadic, so I don't really want to present it as a standard product at this time until that situation changes. But it's always, if you have an interest in this sensor in particular, it's always worth double checking with Andor to see if that sensor is available at that time, because in an occasion, and actually I think it's the case right now, that sensor can be available. The future we haven't quite solidified yet, but we are very much open to conversations. For sure, we think we want to do the 6K 6K sensor from E2V. We see a building demand for this sensor, and also there's one I'm not mentioning here. There's a 9K 9K format from E2V as well, with 8 outputs that we will likely build into the platform at some stage. And sometimes we get demand for STA sensors as well, so we will likely look to STA as a provider down the line also. It's worth pointing out, we launched this camera formally about a month and a half ago, but we actually were working informally behind the scenes with some customers to build cameras before we formally launched it. And there are actually cameras already shipped and in use in China and Antarctica. Sorry. And as it is, the camera is proving very popular. We're now on, I believe we're now in excess of 10 orders in the door in a fairly short space of time. So we're very excited about this camera. We know it's resonating well in the astronomy community. Applications, I've just listed a few potential applications here, but I'm sure there's going to be many that I have not included. It's worth mentioning, in case this is relevant, ASCOM is a Windows standard for astronomy. It's a many-to-many language independent architecture, and it then is used to basically make sure lots of different astronomy devices can talk to lots of different astronomy softwares. So it's worth pointing out all of the Andor CCDs and EMCCDs, including the iKon XL, are now integrated into the ASCOM standard. An interesting one I wanted to flag up here is it's quite a a new venture actually from a company called Red Logics in Germany. They were actually inspired through being involved in the Sophia project that I mentioned earlier. Red Logics had a very central involvement in this, and were inspired actually to try and produce a control system which can be used at observatories. So basically, it's a way of linking the control side, the observatory side, where the detection occurs, to a remotely located uh, user. So in doing this, they actually can provide a host of different ruggedized, embedded small PCs of various form factors. It's a Linux operated system, which I know will appeal to many more astronomers than Windows would. So they offer infrastructure and framework software, application software modules. So this is all at the control side. At the operator workstation side, they've also been quite diligent. They offer controller interface library. You can see there with various programming language bindings, GUI frameworks, or widget library for more sophisticated specific GUIs that are custom. So I recommend if you are in control of a large observatory, looking these guys up, going to them with further questions. But from our perspective, it's worth pointing out that several of our key cameras are now integrated into this Astro.Control platform, including most recently the iKon XL, but also the important iKon cameras are in there also. So I thought maybe to try and round up, I'd use this slide to try and provide an encapsulations of how we recommend different of our astronomy cameras to different applications, and what, depending on what the circumstances are. So I've actually tried to generate such a slide even to train our own sales staff, but I thought it'd be quite useful here as well to try and get the point across. So I'm considering first when people generally have a need for sensitivity. I'm dealing first with slower scan CCD applications. We can either send you down what we would regard as the ultimate sensitivity route, which is our iKon platforms, our iKon L or our iKon M. So it's either 1 megapixel or 4 megapixel, and the iKon M uses the 4710 sensor, the iKon L uses the 4240 sensor, and these cameras are each deep cooled to minus 100 degrees and offer low noise and are based on a vacuum sensor architecture. So that's what we would recommend first and foremost. However, some applications may be on a budget, and we can offer then the same sensors, the 4240 or the 4710, in the Apogee range. Just, not quite as low noise, not as deeply cooled, but nevertheless a back-finned sensor that can be used still for longer exposure applications. Then we have the high time resolution. Sorry, not high, sorry, high resolution, high spatial resolution and field of view. So there are some sensors in here that Andor have not traditionally offered in the iKon range, but are very much present in the Aspen range or the Alta range from Apogee. And so if you're looking towards high resolution capability still on a budget, we might send you down and look towards some of these cameras, but still feeding into very similar applications. But then we have the applications which require speed and sensitivity. All the ones I mentioned earlier: solar, near-Earth object tracking, high time resolution astrophysics, etc., etc. And then, as I've mentioned earlier, we talk about the EMCCD, the iKon Ultra 888, for example, or the Xyla SCMOS. But then we have the camera we featured today, the iKon XL. So we regard this back into, so it's not for high time resolution, but we still regard it as being, the ultimate sensitivity, high resolution, large field of view, and very high dynamic range as well. So it's quite unparalleled in that regard. So that's just a snapshot way of trying to take our fairly extensive portfolio now and breaking them down to different use cases within astronomy. So my final slide. I'm not going to go into any detail here on this webinar on this, but it's more as an indication, as an extension then of what we're doing on the very large area CCDs. We're also working on a new technology, which is going to take the very large area concept, but enable it at very fast speeds and low noise. I'm going to say no more than that at this point, but I would encourage you, if you think you have a need, if you think, for example, you've been looking at the iKon XL, think, I love it, but it's not going to be fast enough. I want the field of view, I want the resolution, I want the sensitivity, but I do need to go faster, then talk to us. We'll fill you in a bit more detail about what we're working on next. But applications I'm considering for this are similar to what we've talked about already for the SCMOS and EMCCDs, just with a much larger field of view.